Next up, we want to look at some examples comparing the washer and the shell method. So in these first two examples, we're going to do both the washer and the shell method, but before we actually do any computations, we're going to use the comparison above in order to predict which method we think is going to work better. So in both of these examples, we've already seen a type of computation. We've computed the volume of this region using either the washer or the shell method previously. But now we're going to do both, and we're going to see which method is better. So let's kind of dive in. So here, R is the region bounded by the x-axis and the curves y equals root x and y equals 2 root x minus 1. We want to find the volume of the region formed by rotating R about the x-axis, using both the washer method and the shell method. So let's draw the region. We've already done the work for this, and part of the reason that I'm recycling some examples here is so that we don't have to spend a lot of time worried about what the region looks like, and instead we can focus on the different methods. So here is, oh, we should give this a color. Here's the square root of x. And we know that 2 root x minus 1 is steeper and shifted to the right a little bit. So it's going to look something like this. And our region here is this region bounded by the x-axis and these two curves. So if we want to think about, maybe we want to think about which method we would prefer to use first. So I want to compute the area of this region. What variable would I prefer to use? And so I want to think about drawing a bunch of vertical lines and a bunch of horizontal lines. So let's sort of trace the lives of some vertical lines first. So if I'm drawing some vertical lines, I notice that kind of on the left here, I'm bounded from above by the blue curve and from below by the axis. But as I keep moving to the right, eventually it starts to be the case that my lower bound is the green curve rather than the axis. So this tells me that if I'm doing any integrating with respect to x, then I'm forced to split up the integral into two pieces. One where the upper bound is the blue curve and the lower bound is the black curve. The other piece where the upper bound is the blue curve and the lower bound is the green curve. So integrating with respect to x maybe doesn't seem like the greatest idea here. In contrast, if I sort of trace out some horizontal lines here, I see it's always the case that the left bound is the blue curve and the right bound is the green curve in this region. So to me, what this is saying is that integrating with respect to y is going to be easier because integrating with respect to y will allow me to just do everything in a single integral. I don't have to break this region up into multiple pieces. So the answer to the first question is we would prefer to integrate with respect to y. The second question that we want to answer is which axis am I rotating about? And I'm rotating about the x-axis here, it tells me. I notice that the preferred variable of integration here is y, and the rotation axis is x. Those are not equal, which tells me that the shell method is probably easier here. So let's make that hypothesis and see what happens. All right, great. So maybe let's do the shell method first. We'll see how it is. And in fact, this is one that we've already done with the shell method. So let's see. So in order to set up the shell method, we're thinking about taking these horizontal red lines and rotating them about the x-axis in order to form some kinds of shells. We know that what we're doing here is we're integrating from the lower bound on y. The smallest y value here is 0. We already did the computation to find that this intersection point occurs with the y value 2 over root 3 and the x value 4/3. And so we're integrating from the lower bound on y, 0, to the upper bound on y, which is that 2 over root 3 number. We know that what we're integrating here is the surface area function of each of the shells. The shells themselves have radius y, so the circumference of the shell is 2 pi y. we need to multiply that by the height. The height is the difference between the x values on the green curve and the blue curve. And so we can go about solving for the x values. We want to solve each of these blue and green equations for x in terms of y. We already did this in a previous video, so I'm not going to go about these details again. But for the green curve, you end up with the x value is y squared over 4 minus 1 plus 1. For the blue curve, you get that the x value is y squared. So we have this integral set up here, and if we go about doing some of these computations, we can factor out that 2 pi on the inside of the integral from 0 to 2 over root 3. We're going to end up y squared over 4 minus y squared is going to give me a minus 3y squared over 4. And plus 1 is just plus 1. Oh, but we're multiplying through by y. So we have cubed and y there. Great. All right, so we have our integral set up. Now we can actually do this computation. This is a fairly straightforward integral for us, and we're going to need a little bit of room here because I'm going to walk through some of these computations. So we'll have 2 pi, the antiderivative of y cubed is going to be y to the 4 over 4. So the 4 and the 4 multiply to give me 16. The integral of y is going to be y squared over 2, and we are evaluating from 0 to 2 over root 3. So at 0, this evaluates to 0, so we can simply plug in 2 over root 3 here, and we get 2 pi times minus 3. Let's see, 2 over root 3 to the 4 over 16 plus 2 over root 3 squared over 2. All right, next we maybe want to simplify a little bit of the arithmetic here. We want to end up comparing the answer that we're going to get from the shell method here to the answer that we're getting from the washer method. And if our arithmetic looks as nasty as this, it's not going to be easy to compare the answers. So let's simplify some things a little bit. And let's see, so we're going to have this 2 pi out front for a little while. If I raise 2 over root 3 to the 4th, I get that 2 to the 4th is 16. Root 3 to the 4th is 9 over 16. 2 squared, this 2 over root 3 to the second power is going to be 4 over 3 all over 2. So we have 2 pi. Let's see, simplifying this first fraction here is going to give me that 3 over 9 is going to give me a 3 in the denominator. The 16 is going to cancel the 16 out in the denominator, and I'm left with a minus 1. So that first fraction simplifies nicely to minus 1/3. The second fraction, the 4 divided by 2, is going to give me a 2 in the numerator, and that 3 stays in the denominator, so that's 2/3. Now, inside the parentheses here, I have minus 1/3 plus 2/3, which is conveniently 1/3. And then 2 pi times 1/3 is 2 pi over 3. Great. So the volume of this region, 2 pi over 3, pretty simple answer. Let's go ahead and check the washer method to see if we can get the same answer out. So this was our shell method. Washer method. All right, so this time we are looking at our purple vertical lines here. And in order to think about what washers these guys are making as I'm revolving them about the x-axis, I need to, as I stated before, break up this integral into 2 pieces. One where the x values range from 0 up to where this green curve starts, which happens to be at x equals 1. And the other from 1 up until the right end point of my region, which is at 4/3 here. So let's see. So integrating from 0 to 1, and I'm adding an integral from 1 to 4/3. On the region from 0 to 1, my washers are actually going to be disks, because I'm just looking at the area between the blue curve and the x-axis. So each of these washers is a disk with radius equal to the y value on the blue curve. And so the surface area of one of those washers or disks is going to be pi times that radius squared. So pi, the y value on the blue curve, is the square root of x. So we're looking at this area here. For the interval where x lies between 1 and 4/3, I have a washer this time where the outer radius is the blue curve and the inner radius is the green curve. And so what I need to do is I need to take pi times the outer radius squared. Outer radius is again root x, minus the inner radius squared. So the inner radius is now the blue curve, which is 2 root x minus 1 squared dx. So here already, just in this kind of setup, we can see that where the shell method has a nice advantage. With the shell method, we wrote down a single integral. With the washer method, we had to write down 2 different integrals in order to capture this volume. All right, continuing on with this washer method, we want to simplify some of these integrals a bit. So we're going to have the integral from 0 to 1. Root x squared is nice, that's just x. Integrate from 1 to 4/3 of, let's see, so we're still going to have pi here. Root x squared is x. 2 root x minus 1 squared is going to be 4x minus 1. First integral, pretty straightforward. That's going to be pi x squared over 2, evaluated from 0 to 1. Second integral, we still need to do a little bit more work in order to simplify the integrand, but maybe we can factor the pi out first. 1 to 4/3 of x minus 4x is going to give me a minus 3x plus a 1. Nope, plus a 4. All right, again, relatively simple integrand here, so we can do some evaluation. So on this first term, this pi x squared over 2, evaluated from 1 to 0, I first evaluate at 1 to give me pi over 2. I then evaluate at 0, and that gives me 0. Great. So plus pi. Now this second antiderivative here, the antiderivative in the second term, is going to be minus 3x squared over 2 plus 4x, and we're now evaluating from 1 to 4/3. Certainly not the neatest computation we could do, but let's push through it. Let's see, pi over 2 is going to float around out front for a while, plus pi times, evaluating at 4/3, we're going to have minus 3 times 4/3 squared over 2 plus 4 times 4/3. Now we need to subtract the thing evaluated at 1. So evaluating at 1 is nice and simple here. We're left with minus 3/2 plus 4. All right, and now it's time for some arithmetic. Let's see, we've got pi over 2. We have plus pi times this first fraction here, this minus 3 times 4/3 squared. Let's see, so the 4 squared gives me a 16 in the numerator. The 3 that's in the numerator here is going to cancel out with one of the copies of 3 in the denominator, but that leaves me with another 3 in the denominator, so I'm left with minus 16/6 here. Let's see, 4 times 4/3 is going to give me a positive 16/3. The minus 3/2 gives me a plus 3/2, and the minus 4 gives me a minus 4. All right, let's simplify some things still. Pi over 2 plus pi times minus 16 over 6 is minus 8/3, plus 16/3 is going to give me a positive 8/3. 4, we want to convert that into halves probably, so that's going to be 8/2. 3/2 minus 8/2 is going to be minus 5/2. All right, we're getting close. We are getting close. So pi over 2 plus pi times 8/3. We need to convert these fractions into sixths. 8/3 is 16/6. 5/2 is 15/6. So 16 minus 15 gives me 1/6. And now I notice that, well, I've got pi over 2 plus pi over 6, and that is exactly 2 pi over 3. So in the end, both of these methods gave us the same answer. We've got 2 pi over 3 coming out of both of them for this volume, which is great. If we got different answers, then we would have kind of a problem here. But we got the same answer. But what I really want to emphasize is observe how different these two processes were. The shell method was both simpler in terms of the integral and also kind of simpler in terms of the arithmetic that we had to do. You can see we had like 3 whole lines of just computation here, whereas in this first shell method, we really only had 2 at most. So not so bad. But also notice the different ways by which we got to this 2 pi over 3 number. In the washer method, we were adding up a bunch of different numbers. We had fractions all over the place, whereas we only had a couple of different fractions in the shell method, and yet both of these approaches brought us to this same sort of conclusion here. So that's kind of nice. It's one of the things that I find really neat about this, is how these two methods are so very different, and they get you to the same answer in just these very different ways. All right, that's where I think I'll leave this video. Next video, we'll cover the next example. I want to maybe encourage you to try the next one on your own and think about which method you think would be easier. Here our hypothesis was confirmed. But next video, think about which method will be easier, and also maybe try both the shell and the washer method for yourself and compare to what I get.